You've seen the magic, right? Generative AI pulling incredible images out of thin air, writing code, holding conversations. It really does feel like magic, but it's not. What we're actually seeing is engineering, just on a scale that's almost impossible to wrap your head around. So today, we're going to get an all-access pass to the factory floor. We are pulling back the curtain on this unseen machine to show you how these models are really built. All right, let's start the tour. First up, we're going to look at the universal blueprint that, believe it or not, almost every modern AI is built from. Then we'll head over to check out the raw materials and the absolute revolution happening in data engineering. After that, we'll see how these models are being taught to actually think ahead, not just react. Then it's down to the engine room, the massive supercomputers that power this whole operation. And finally, we'll see the assembly line in action, how this all comes together to create the mind-blowing audio and video that we see. So what's the big secret here? You'd think that an AI that generates text and an AI that generates video would be, completely different animals. But here's the big reveal. They're not. The fundamental blueprint, the core architecture for pretty much all of them, has converged on one surprisingly simple, incredibly powerful idea. And that one idea, it's the transformer architecture. Now, this thing was born in the world of language processing, but it turned out to be so ridiculously good at finding patterns that it's now the universal chassis for almost every single state-of-the-art model out there. If you think of this as an AI factory, the transformer is the main assembly line. So how does this universal blueprint actually work? Well, it really boils down to a simple three-step recipe. Step 1, tokenize. You take reality, words, pixels, sound waves, whatever, and you chop it up into discrete little digital pieces called tokens. Step 2, transform. You feed those tokens through that transformer assembly line we just talked about. And step 3, scale. You just do this with more data and more computing power than you can possibly fathom. Tokenize, transform, scale. That is the heart of everything we're seeing today. Okay, so every factory needs raw materials. For an AI, that material is data. And we have absolutely entered a new era here. It is no longer about just hoovering up the entire internet and hoping for the best. No. Fueling these models has become its own incredibly sophisticated engineering discipline. Just a few years ago, the philosophy was simple. Bigger is better. The whole approach was just to scrape the entire web, all the junk, all the good stuff, and just cram it into the model. But now, with cutting-edge datasets like FineWeb, the game has totally changed. It is all about precision engineering. The new mantra is that the quality of your data, its purity, is way more important than the raw quantity. Now, what's really fascinating is how they find that quality data. Check out this brilliant trick called rehydration. For years, engineers would deduplicate the web, right? They'd throw away any repeated content. But then they had this huge realization. If something is repeated a million times online, like a famous poem or a key piece of code documentation, it's probably pretty important. It's high-signal stuff. So rehydration cleverly uses that repetition as a vote for quality, boosting the good stuff without the insane cost of processing the same exact text over and over again. It's genius. And this right here gives you a perfect look at the nitty-gritty work involved. These are the Gopher rules, just a set of simple but unbelievably effective filters for scrubbing data clean. Think of them like bouncers at a club for data, kicking out any documents that are too short, too long, filled with gibberish, or are just messy code dumps. It might not sound glamorous, but this kind of work is what separates a good model from a truly great one. So we've got our pristine, high-quality raw materials. Now we need the right machinery on the assembly line itself, the learning algorithm. And this is where we're seeing another huge shift. For years, the goal was simple: predict the very next word. But the new frontier is all about giving the AI a glimpse of the future, teaching it to plan instead of just react. But that's a huge challenge, isn't it? How do you teach a machine to plan ahead when its entire world is built on just guessing the next word in a sequence? This standard approach, next token prediction, is fundamentally short-sighted or myopic. It's great at short-term stuff, but it often gets lost and kind of loses the plot when it needs a long-term strategy, like writing a coherent story or a complex essay. So the crucial pivot here is this move from reaction to intention. Instead of just predicting the very next word on the path, these new future-aware techniques force the model to look up and actually consider the destination. It's the difference between just putting one foot in front of the other and actually knowing where you're going. And here are just a few of the clever ways engineers are making this happen. For instance, a technique called CocoMix doesn't just predict the next word, it also has to predict a high-level concept that's coming up later in the text. Other methods make the model predict, say, the next 3 or 4 words all at once, forcing it to think in phrases. It's all about tricking the model into developing a sense of foresight, a little peek at what's to come.
All right, we've seen the blueprint and the raw materials. Now let's talk about the physical factory building, the hardware. And I want to be really clear about this. We are not just talking about a room full of powerful computers. The very architecture of the supercomputer is now a crucial, inseparable part of the AI model's design.
And to really get why, you have to appreciate the staggering scale we're talking about. Today's biggest models have over 1 trillion parameters. You can think of those as tiny internal dials the AI tunes as it learns. 1 trillion. That number is so vast, it is absolutely completely impossible to fit on any single computer on planet Earth. The only way to do it is to lash together thousands of them into one single coordinated machine.
Now, the strategy for taming this beast is called 3D parallelism. And it's a brilliant way of slicing up that giant AI model in 3 different dimensions so it can be spread across thousands of GPUs. You can slice it horizontally within a single layer, you can slice it vertically by putting different layers on different machines, and you can slice the data itself, giving each machine its own little chunk of the problem. It's how you make the impossible possible.
And this is where the physical world slams right into the digital one. The network connecting all these machines isn't just a random tangle of fiber optic cables. It's a meticulously designed architecture. A rail-optimized topology is like building a dedicated express highway between the specific GPUs that need to talk to each other the most. It proves this fundamental point. The physical layout of the building directly enables or limits the power of the AI. Okay, now for the payoff. We have toured the factory. We've seen the 3 pillars: the precision data, the future-aware algorithms, and the orchestrated supercomputer. So let's see how they all snap together to create the final products, these incredible audio and video models that are literally changing our world. Let's start with audio. How do you apply that universal blueprint to something like sound? Well, remember, step 1 was to tokenize reality. For sound, that magic is done by something called a neural audio codec. It's a specialized AI, and its only job is to listen to a complex sound wave and break it down into a stream of discrete digital tokens. Once you have sound tokens, well, you can train a large model to predict them, exactly like a language model predicts word tokens. And the engineering behind this is it's beautiful. To get that rich, high-fidelity sound, they use these clever tricks like residual vector quantization, which is kind of like stacking layers of simple dictionaries to describe incredibly complex sounds. They even use custom math, like this snake activation function you see here, specifically because its wavy shape is perfectly suited for modeling the natural periodic waves of sound. It's so cool. And now for video, where the complexity just goes completely off the charts. The Open Sora project gives us a perfect peek into the strategy. See, you don't teach a model to make a movie by showing it a feature film. You put it through school. It's a curriculum that starts with the absolute basics: short, blurry, 2-second clips, just enough to learn physics. Then it graduates to slightly longer, clearer clips to learn about objects. And only at the very end does it learn about cinematic detail. It's how you teach a machine to handle almost infinite complexity. And this quote, this really just hammers home the central point of this whole factory tour. The supercomputer, the network topology, the parallelism strategies, they are not just IT support. They are the laws of physics for the AI engineer. They are the architectural constraints that dictate what can and cannot be built. The digital model and the physical machine are not 2 separate things. They are one and the same. So where is all this engineering heading? Well, the next great frontier, the real moonshot for this entire field, is building a single any-to-any model. One unified architecture that can fluently translate between text, images, audio, video, maybe even brainwaves, who knows what else. We've seen the blueprints for all the different assembly lines in the factory. The ultimate question now is, how do we connect them all into one seamless, unbelievable machine?